Okay, if we understand the idea of the first principal component, then understanding the second and third and nth principal component should be pretty simple. We have our data in whatever dimension it is. And the first principal component is a line that you draw so that when you orthogonally project your points onto that line, the projections are as spread out, are as varied as possible. The second principal component is going to be a line orthogonal to the first principal component. And again, we're trying to get our data to be as spread out as possible. We're trying to explain or capture as much variance as we can. And there's no great way to show this on a two-dimensional plane because once you have drawn the first principal component, there's only really one way to draw the second principal component. I mean, there's only one sort of vector that's orthogonal to the first one, but that is the idea. So the first principal component captures as much variance as possible. The second principal component is orthogonal to the first and captures as much of the remaining variance as possible. And the idea of orthogonality, I mean, stating this just informally, but the idea is that if vectors are orthogonal, they store different pieces of information. Like if you think about a map, you've got the north-south direction and you've got the east-west direction. These vectors are storing different pieces of information and they are orthogonal. They hit each other at a right angle. So the idea that we're not storing redundant information is why we have this orthogonality requirement. And once we've seen the second principal component, there won't be any surprises. The third principal component will be orthogonal to the first and the second, and will capture as much of the remaining variance as possible. So the way these principal components are defined, each of them is less helpful than the one before it. The first component gives you the most information. The second component gives you the second most information. The third component gives you the third most information, and so on. And we'll ask, so when do we stop? When do we think we've hit the point of diminishing returns? We'll discuss that in a later video. For now, I'll just show you a few pictures. Because the first two principal components, this is two-dimensional, we can look at the data projected onto the first and second principal components. We've looked at the data projected on the first component, that was a number line. If we look at the data projected onto the first two components, that's a plane. So I'm just going to look at a few examples again using those books. I don't want to dwell on the code. Um, I'll point out now that we've got this standard scalar. It will make more sense to talk about that in a later video. I'll also point out that it's really easy to perform PCA in Python. It's just right there in sklearn. So the actual code to perform this analysis is extremely simple. And the rest of this is creating graphs and stuff like that. So at the moment, let me see if I can find my book. Here we go. At the moment, we've again got Agatha Christie and Amanda Quick, just using those as my default examples. Let's run this code and perform the PCA. And you see, I've said that I want to look at this in 2 dimensions. So here's our projection in 1 dimension. That's pretty impossible to see, isn't it? But we saw that our Agatha Christie was all together and our Amanda Quick was all together. Here is the projection onto 2 dimensions, the first and second principal components. And we see differences. And these differences don't necessarily have a single clear explanation, because again, the components don't have a single clear explanation. There isn't a genre component and a style component and a decade component. Some components might be sort of correlated to one of those. You know, the first principal component looks like it's sort of correlated to genre, but it's very imperfect and very imprecise to talk about that kind of correlation. Um, talking about this very naively, here's one situation that would explain the graph. If the first component was sort of correlated to genre, and the second component was sort of correlated to authorial vocabulary, then a graph like this, where all the Agatha Christie novels are grouped together in the second component, whereas the Amanda Quick novels are spread far apart. Something like that could be explained if Agatha Christie has a limited vocabulary and Amanda Quick has a varied vocabulary. I'm not saying that is what's happening. I don't know what's happening. I'm putting it forward as one possible situation that might give us the graphs that we're seeing. And Agatha Christie, this is not a slight against her. She does use a pretty limited vocabulary. My older brother, who teaches English as a second language, has remarked to me she's very popular for people who are learning English for exactly that reason. Having said that, I don't think that's actually what's happening here. Because let's go back to this and let's add Rex Stout into the mix. Rex Stout is an American mystery author. He has an extremely distinctive vocabulary. There are words he loves that Agatha Christie and Amanda Quick don't really use. So if this were sort of explaining the PCA, then when we look at Rex Stout versus Agatha Christie, they'll be separated vertically. If the second component is really looking at distinct vocabulary, Agatha Christie and Rex Stout will have very distinct vocabularies and will be able to see them far apart from each other. And that's not what we're going to see. I mean, of course, I've run these simulations before. If we run this again with Rex Stout in there, Rex Stout and Agatha Christie are just mixed together on this vertical component, which suggests that maybe this second component doesn't have any very easy to understand meaning or interpretation. It's not representing distinct authorial vocabulary, or we'd be able to keep Rex Stout and Agatha Christie separate. It's not, representing differences in American versus British vocabulary, again, because these people are grouped together. It's not representing, the fact that people writing in different eras use different words because Rex Stout and Christie were writing in different eras and they're all blurred together. So it's very hard to know exactly what this second component means. And that's quite typical of principal component analysis. One thing we will see, though, let's throw in Faust. When we were looking at the first dimension and we looked at Faust part one and part two, we were surprised, or at least I was surprised, at how they did not cluster together in the first dimension, in the first principal component. Let's take a look in two dimensions. Hmm, this is okay. Uh, so every time you add new data, it changes all the principal components. What I was expecting was that Faust Part 1 and Part 2, they're very different in the first component, but I was expecting them to be similar in the second component. Obviously, that's not what we're seeing. Let me Let me find my folder. Okay, I don't know if this is visible currently, but I'm going to take all my books and I'm going to throw them all into this folder together. And now I'm going to rerun the PCA. And maybe we'll get what I was expecting to get. Tum tum tum. The bigger the data set, the longer this takes. Okay. Okay. So with all of this data, now I'm seeing what I was expecting to see earlier, which is that Faust Part 1 and Part 2 are quite different in the first principal component, but seem to be similar in the second principal component. Um, One dimension is not necessarily enough to explain the data. Two dimensions are not necessarily enough to explain the data. And what I inadvertently demonstrated, but it's important to know, again, the PCA is generated by the data. So when you add new data, the PCA changes. In this particular case, adding new data brought Faust Part 1 and Part 2 closer together in the second component. It's not a guarantee that something like that will happen, though.